So here's a little bit more about circular motion and forces, and this includes tangential acceleration. So we've already talked about how any object moving along a curved path must be accelerating towards the center of curvature, and we call that centripetal acceleration, which causes the direction of the object to change. Today, we're going to also talk about tangential acceleration. So any object moving along a curved path, it might be accelerating tangent to that path. And the tangential acceleration changes basically the speed, changes the magnitude of the velocity, which is speed. So just to illustrate, imagine this is a path of some particle, and here is the particle at this particular moment. Because it's on a curved path, it must have a centripetal acceleration pointing at the center of curvature. And let's suppose that it's also, not only is the direction changing due to the centripetal acceleration, but let's say that its speed is changing. Um, it could be increasing or decreasing. And in this case, let's say it is going this way and it's increasing in speed. We would draw the acceleration tangent to the path. And so tangent means a tangent line would be a line that touches the curve at this point where the object is located. And so it would have an acceleration right here. And we would call it tangential acceleration. That's an A with a subscript of capital T. Okay, let's try out an example here. We have a ball at the end of a string and it's being rolled around vertically around this path here. The ball has a mass 0.3 kilograms. The length of the string is 0.90 meters. The speed at this particular position where the ball is 12 meters per second. And the angle shown here is 48 degrees. First thing we'll do is draw a free body diagram, then determine the tension force in the string, and then figure out the tangential acceleration. So it's important to note that as the ball goes from this position, goes up here, the speed is slowing down as it goes up to the top. So let's draw that free body diagram. Draw it right here. It has gravitational force mg, and the string is pulling it in this direction, Ft. It's important to note the angle. So this is the direction of the tension force. And so if I kind of draw a straight dotted line here, this is that angle theta. And you can kind of tell that by looking here. Let's go back. Okay, so I think you can see here that this is the angle theta, right? These are alternating interior angles or alternate interior angles. And so this is that angle theta. Now it's important to note two things. There is a centripetal acceleration in that direction. The centripetal acceleration is changing the direction of the ball and it's pointed towards the center of curvature. So we have centripetal acceleration in that direction. And so therefore we want to keep the tension force in that direction. We don't want to break that one up into components. But there's also a tangential acceleration. And since the speed of the ball is slowing down, the tangential acceleration is pointed in this direction, tangent to that curve. And so I'm going to trace that on here. Okay, centripetal acceleration this way, and there must be tangential acceleration this way. And so what we do want to break up the gravitational force into components. and we want to have one of the components going this way. So we can kind of construct a triangle here or kind of construct a triangle here. And so we can get a component going along with the tangential acceleration. The other component will be in line with the centripetal acceleration. So I'm gonna copy this and trace this down here. So remember that you want to keep your free body diagram intact because that one is worth points. If you're going to break it up into components, do that somewhere separately. And I think I'll make my triangle this way. So here's one component. This will be mg something. And let's bring this here. I've kind of written over that. Let's just erase that. This is the force mg. Okay, so these are the components. Or this is my triangle, in other words. I'm showing it like this for now, but I'm going to change this. But here's that angle theta. I think we can all see that these are equal angles. And so since this is the adjacent side, this component here, this is the cosine, and this is the opposite side to that angle theta. So this is sine. Now on the free body diagram, we will put this over here. So can I just steal it? There we go. Oh, and it's taking that with it. I made a mess here, but you guys can figure out what I'm trying to do here. mg sine theta is here. Now, because I've broken it up to components, I really need to get rid of this, but I just wanted to illustrate where that came from. These are the components of the gravitational force. Cool, so now one of the components is along with in the direction of the tangential acceleration, and mg cosine is with the centripetal acceleration here. Oh, let's go to part B. We're trying to figure out the tension force. We'll need Newton's second law. And by the way, so because the tension force is in the same dimension as the centripetal acceleration, we will write F equals mac. And I'm just going to come down here and do part C. For the tangential acceleration, we also want to use Newton's second law, but this is not a centripetal acceleration, it will be the tangential acceleration. Okay. This is mv squared over r. And the necessary forces that go here is Ft and mg cosine. Ft will go first here. Subtract mg cosine theta. Cool, and I've forgotten what we're solving for. We're solving for Ft. So this will be mv squared over r plus mg cosine theta. And we're just plugging in some numbers here. Let's move that down. So the mass is 0.3. Speed is 12 squared. The radius is equal to L, which is 0.9, plus 3 cosine 48 degrees. Cool. As usual, I don't have my calculator ready. Let's get that here. And add 3 cosine 48. Okay, looks like 50 is the tension. Cool. And then over here, we'll just bring our component and the tangential acceleration. So mg sine theta is equal to m times the tangential acceleration, cancel m, and it's just g sine theta. That's g times sine of 48. 7.43. Looks good to me. All right, let's continue. Okay, so this one is over a conical pendulum. Pendulum is a ball on a string that swings back and forth, just constantly goes back and forth, this way and that way. That's a pendulum. Conical pendulum does the same thing, but it moves, the ball moves in a horizontal circle such that the string kind of shapes out a cone as it swings. And so it kind of swings this way and back that way. So the string is length L, some angle theta. The ball or the bob has a mass m. And so using those and fundamental constants, well, first of all, we'll draw a free body diagram, but then determine the tension force in these terms and figure out the speed of the ball. And so let's draw a free body diagram for this. So the ball is here, gravitational force mg. The string is pulling in this direction. And if that's the angle, of course the angle is here. Let's label it, this is ft. Here's the angle theta. Now it must be the case that there is a centripetal acceleration pointed towards the center of that curvature. So I will bring this here. There's a centripetal acceleration here. And so, of course, we've got to break up one of these forces into components. mg is at a right angle with the centripetal acceleration, which is fine. It's the tension force. And so I'm going to cheat and copy this. Remember that if you are breaking up a free body diagram into components or a force into components, that you've got to do that separately from the free body diagram. Leave this alone. That's worth points. This one that we do here is not. And so we'll break this up into components. You know what, I'll just, well, before I get rid of it, there's a component this way, and there is a component going up this way. So here's the angle theta. This is going to be, since this is the adjacent to that angle, this is ft cosine theta, and this one will be ft sine theta. I don't want to have both. It's one or the other. Cool, looks good to me. We have two forces perpendicular to the centripetal acceleration, and we have a force, a net force, that is along with the centripetal acceleration there. So let's do part B. So what is the tension force? Well, I think for that one we'll do the vertical. Newton's second law. We can say there is no acceleration vertically. So it's ft cosine theta minus mg equals 0. And so ft cosine theta equals mg. This is mg over cosine of theta. I'm trying. This is really, this pen here on this tablet is really slippery. Cool, and there's no numbers. We do have it in terms of m, fundamental constant here, g, and theta. So this is done. That is the tension force in those terms. And let's do c, the speed. Well, let's see here. We can do Newton's second law for the centripetal acceleration here. That's ft sine theta equals m v squared over r. And let's see, we can't keep ft, although we can substitute what ft is down here. And so I think I'll just do that first. This would be mg over cosine theta. Usually a good idea when you substitute an expression here for example, ft that we just put in parentheses. It's not entirely necessary in this case. V squared over r. And so we have mg. Now sine over cosine, I like to just write tangent. That's one of those trig identities. So sine theta over cosine theta is tangent theta. So mg tangent theta equals mv squared over r. We can cancel an m. And so this is almost finished here. I'm going to rearrange this. R g tangent theta is equal to v squared. Now, before I take a square root, I'd like to substitute something for r. Now, I know they let us use L, but r is not L. So if you look here, L is this length here, but the radius of this curvature is this much. If I erase this here, might have been better to do it on this side. Here is that radius, r. So L is not equal to r, but we can make an expression for it. The sine of this angle is the opposite side, opposite length, over the hypotenuse. And so sine of theta is equal to r over L. I'll do that here on the sine. The sine of theta is r over L. All right, so pause it and think about that if that's confusing you. That we're just looking at the triangle here and making a relationship. So r is just L sine theta. And this is in terms of L and theta, so we're going to substitute this into our equation. This is L sine theta, should say LG sine theta tangent theta equals v squared. And so we can just take the square root LG sine theta tangent theta equals v. And that looks good to me.